Hi everyone, and welcome to Lesson 4, Igneous Rocks and Intrusive Activity. So this covers Chapter 4 in your textbook, and your pages are listed right there. Now, as a little bit of a warning, there's a lot of terminology with the next several chapters, so please beware. Geologists definitely like their jargon. We have a different term for almost everything, but that jargon is very important in understanding what a geologist is talking about. So please make note of some of our technical terms, and if you have questions, let me know. So we're going to go ahead and dive right on into the beef of this chapter. So let's get started. Magma is the parent material of all igneous rocks. So igneous rocks form as molten material cools and it solidifies. That's going to make our rock. Now, some of the general characteristics of magma. It forms by a process called partial melting that is going on down inside the earth. Now, as magma reaches the surface, it is called lava. I won't be quite as particular about the difference between magma and lava like I am mineral and rock, but it is very important to distinguish the two. So rocks that are formed from magma at the surface are classified as extrusive. So it was magma, it's been extruded, becoming lava, so it's been extruded. So extrusive or volcanic rocks. Now, rocks formed from magma that crystallizes at depth are termed intrusive because they're inside the earth, or plutonic rocks. Alright, so we're going to do just a little bit of testing our knowledge already. We're going to decide whether there are intrusive or extrusive rocks. So in the upper right hand image, we see an underwater volcano erupting off of Tonga's main island. So that was back in 2009. So would the rocks that are created from this sort of eruption, would they be intrusive or extrusive? They're going to be extrusive rocks, right? Even though it's underwater, it's still at the surface of the earth. So it's going to be producing those extrusive rocks. Now, if you look at the bottom left-hand picture, that is an image of Kilauea erupting, and that's off of Hawaii's main island. For the top arrow, that's actually pointing to magma inside the volcano. So is that going to be producing intrusive or extrusive rocks? Very good. It's intrusive rocks because it's inside the volcano. Now, when it's flowing out on the surface where that other yellow arrow is, those would be our extrusive rocks. Let's go ahead and move on. So we're going to talk a little bit more about the nature of magma. So completely or partially molten material which cools and solidifies forms our igneous rocks. Now it has three parts. It has solid, liquid, and gases. Now the liquid part, that's just what we call the melt. The solids are any silicate minerals that were inside the magma chamber that are starting to crystallize out. And then we have some of our different gaseous components. So we have water vapor, carbon dioxide, and sulfur dioxide. Now those are the three most common gases that you're going to find in magma, but there are plenty of more, and we'll learn a little bit more about some of the gases you can expect in volcanoes when we get to our next chapter. Alright, so crystallization of magma. So we're going to generate different type of silicate minerals. So just a little bit of a review. What exactly are silicate minerals? Remember, they have to have silicon and oxygen. Now within that we have two different divisions. We have our ferromagnesian and our non-ferromagnesian silicate minerals. It just depends on their composition, whether or not they have iron and magnesium, or if they do. Alright, so we're going to start moving on. So cooling of the magma results in the ions arranging into orderly patterns in various minerals. Now the size, shape, and arrangement of the mineral grains give an igneous rock its texture. Now texture is going to be a common term that we use for igneous, sedimentary, and metamorphic rocks. But igneous rocks are most often classified based on their texture and their mineral composition. Alright, so talking about some of our different types of igneous textures, it is used to describe the overall appearance of a rock based off of the size, shape, and arrangement of its interlocking crystals. Now, there are several factors that affect the crystal size. The first one is going to be the rate of the cooling of the magma. So, slow cooling is going to promote larger crystals. Now, the faster it is, the smaller they are. So, if you look over, let me grab my pen real quick. If you look over here, where we start up here with slow, you can see that you can make out individual mineral grains. Now, by the time we get into the fast intermediate, you can't make out any, and eventually once you get all the way down to the fast section, we have volcanic glass, so you can't see anything. Now, another factor that affects the crystal size is the amount of silica present and the amount of dissolved gases. Alright, now getting into our different types of igneous textures, our first one is aphanitic. Aphanitic is a fine grain texture that is formed from rapid rate of cooling of lava or magma. So you can't see the individual grains without a microscope. Now, it may contain what we call vesicles or voids, and the most common rock is basalt. Next, we have phaneritic. Phaneritic is what we consider coarse-grained, so this is slow cooling. Crystals can be identified without a microscope, and grains are commonly equal in size. So this is pretty typical of granite. Next is going to be porphyritic, so minerals form at different temperatures as well as different rates. So large crystals are what we call phenocryst, will be embedded in a matrix of smaller crystals called ground mass. So if you look at the image over here where I have the word phenocryst, you'll see this arrow, it's pointing to these white specks. So those are individual mineral grains that we see in here. And those actually cooled much slower than all of the black around it. So all the black is actually a mineral that cooled so quickly that you can't actually make out the individual grains with the naked eye. So this is a mixture of coarse-grained and fine-grained together, creating this porphyritic texture. Now, the most common rock of this type is a porphyry. Alright, so next we have glassy. So glassy is rapid cooling of molten rock. It's mainly from a viscous granitic magma. We'll talk a little bit more about that later. And the most common rock is obsidian. Now, types of igneous textures, the next one is going to be pyroclastic. So these are fragments ejected during a violent eruption. Textures appear to be more similar to a sedimentary rock, and the most common rock type is a welded tuff. So in these images you can see individual fragments. So as the volcano erupted, these fragments were ejected into the air, and in some places, as they were laid down, they later became all cemented in there together. But this fragmental appearance is what gives it that pyroclastic nature in the texture. Alright, next is pegmatitic. This is exceptionally coarse grain. It forms in late stages of crystallization, and most have compositions that are pretty similar to granite. The most common rock is a pegmatite. Now, in this image, the best thing about it is you have to look at what is used, sorry about that, what is used for scale. So they have a rock hammer down here. So that's about the size of my forearm, that wooden handle part. So some of those tourmaline grains that you see there are at least a foot long, if not larger. So absolutely massive and gorgeous. Alright, so the next one is vesicular. So spherical voids or vesicles are left by escaping gases. And the most common rock is pumice, but we'll also see this in scoria. Now, for all of our igneous textures, there's a different type of environment of formation, whether that was fast cooling, slow cooling, surface, plutonic body, it all changes, so make sure you're familiar with each type of environment that texture represents. Alright, now getting into our different types of igneous compositions. So there's two primary types of igneous compositions. We have dark or our ferromagnesian silicates, which make up our mafic rocks. A typical rock is basalt, and its compositionally has no quartz, mostly calcium feldspar, and our dark silicates. So some of those would be olivine, pyroxene, amphibole, and biotite mica. Now for our light or our non-ferromagnesian silicates, we have felsic. Our typical rock type is granite, and it's compositionally quartz, muscovite, and feldspars. So just comparing these two rocks that we have images of, we can see that the color of this one is light, while this one up here is dark. So one's mafic and one's felsic. Alright, so now getting into a little bit more about granitic versus basaltic compositions. So granitic are our light colored silicates. It's referred to as being felsic because it has feldspar and silica, so it's rich in silica, and it mostly makes up the continental crust. Now, basaltic compositions are dark silicates and calcium-rich feldspars. It's referred to as being mafic because it has a lot of magnesium and iron. It's darker and denser than our granitic rocks, and it makes mostly our oceanic crust. Now we do have a couple of other compositional groups. We have our intermediate group, which is also referred to as andesitic in composition. So it contains at least 25% of dark silicate minerals. This is often associated with volcanic activity. So the sample that we have over here, this is just what we refer to as a diorite. So it has that salt and pepper texture, so it has about 25% or so of those dark mafic, dark colored silicates. Our other compositional group is ultramafic. It's common of peridotite, and it's very rare, so you can just see exactly how dark this is. Now, silica content can be used as an indicator of different types of compositions. So silica content in crustal rocks can range anywhere from about 45% to 70%. Now, silica influences a magma's behavior because granitic magmas, which have high silica content, are viscous. That means they're really resistant to flow. So it's going to be flowing something more similar to honey. It's liquid at temperatures as low as 700 degrees Celsius. Now, basaltic magmas are low in silica. They're much more fluidal, so they're less viscous, so it flows a lot like water. And it's going to crystallize at much higher temperatures than what our granitic magmas do. Alright, so this is a great chart that shows how silica can be used as an indicator of our composition. So down here where we see the star, We have up to 75% silica and as low as 40%. So our ultramafic have the least amount of silica, while our felsic have the most amount of silica in them. Alright, so we're going to talk about naming of our different igneous rocks, and we're going to go through several different types. First, we're going to start off with our felsic rocks. So these are our light colored ones. We have granite, which is phaneritic, which means that we can see the different minerals in it. So it's 20 to 25% quartz and about 50 to 65% of feldspars. It can sometimes have a porphyritic texture. It's typically a byproduct of mountain building. It's very abundant. We have it here in Missouri. The term granite can cover a whole wide range of different mineral compositions. It's kind of a trash can term. And it's pink to light gray, and it's formed from large intrusive masses. So this is an intrusive igneous rock. Next we have rhyolite. So it is the extrusive equivalent to granite. So it may contain glass fragments, which is what you see in this image. Those little black specks are little bits of glass that are incorporated into it. It's aphanitic, which means that you can't see it with your eyes, or you can't see the individual mineral grains with your eyes. It's less common and less voluminous than granite. Now, it's an extrusive equivalent to granite. So if this was not extruded out onto the Earth's surface and it was cooled and crystallized in the Earth, it would have been a granite. But because that volcano never contained it and it was extruded, it becomes a rhyolite. Alright, next is going to be obsidian. Now, this might be an exception to the rule of looking at them and determining whether it's felsic or if it's mafic, because obsidian is black, but it's actually a felsic rock. So it can vary from black to red, and it has that glassy texture. Alright, next is going to be pumice. So pumice is a volcanic extrusive rock. It's glassy to vesicular, which means it has all those voids from escaping gases. It's a frothy mass and can actually float on water. It's typically light gray in color. Alright, so moving into our different types of intermediate rocks. First we have andesite. So it is fine grained or aphanitic, which means you can't see it with your eyes. The volcanic origin. So volcanic is another term for extrusive rocks. It often can resemble a rhyolite, and it's medium gray in color. Now these two images here have a green hint to them, and that's pretty common as well. Next is diorite. So it's the plutonic equivalent of andesite, which means it is the intrusive equivalent of andesite. So if this magma was extruded onto the Earth's surface, it would be an andesite and not a diorite. It's coarse grained, which means it's phaneritic. Again, it's intrusive. It primarily has sodium-rich plagioclase and amphibole, and it has that salt and pepper coloration. Alright, next we have basalt. So we've moved into our mafic rocks. So it's fine grained to occasionally porphyritic. It's volcanic, which means it's extrusive. It's composed mostly of pyroxene and calcium-rich plagioclase feldspar. It's dark green to black, and it is in oceanic crustal rocks. Alright, now gabbro is the intrusive equivalent of basalt. So again, if this was extruded, it would create basalt. It's composed primarily of pyroxene and calcium-rich plagioclase feldspar. and it makes up a significant portion of the oceanic crust. All right. Next are our pyroclastic rocks. So these are fragments that were ejected during a volcanic eruption. So some of our different varieties, we have tuff, which is ash-sized fragments. We have volcanic breccia, which are particles that are larger than ash. So this sample right here, that is our tuff. While sample B over here, that is our volcanic breccia. Alright, so we're going to do a little test your knowledge. Describe the composition of igneous rocks with compositions at A and D. So at A, what I could expect to see would be muscovite, quartz. So I'm seeing that for A, it's this line, and we're looking at it in this direction. So I see muscovite, I see quartz, it could have potassium feldspar, it could have plagioclase feldspar, biotite, and amphibole. So this is going to be felsic. Let's see how great my writing with this is. Alright, now at D, that's going to be this sample, and we're looking at it in this direction. So it could have sodium-rich or calcium-rich feldspar, it has pyroxene, and it has olivine. So this is going to make up our ultramafic. Ultramafic rocks. Now, would you ever expect to find quartz and olivine in the same rock? Now, our quartz by our percent by volume, that's this line here. And you can see that as we get into more mafic rocks, we actually have that quartz, it fizzles out. So no, and we'll talk a little bit more why you're not going to get quartz and olivine in the same rocks. Alright, so this again, it just goes into some of the different types of environments, so you can review this if you want. Now, talking about the origin of magma. So this is a pretty controversial topic between geologists. So generating magma from solid rock. So it's produced when essentially a solid rock and the crust and upper mantle melts. Now the role of heat is very important. So temperature increases with the Earth's upper crust, which is called the geothermal gradient, and it averages between 20 degrees Celsius and 30 degrees Celsius per kilometer. So rocks in the lower crust and upper mantle are near their melting points. Additional heat actually to cause the rocks to melt can come from friction at subduction zones, heating as rocks are descending down into the mantle, and heat rising from hot mantle rocks. Now the role of pressure is pretty important as well. So an increase in confining pressure, so that's pressure in all directions, can cause an increase in a rock's melting temperature. So this conversely, reducing the pressure will lower the melting temperature. Alright, next we have the role of volatiles. So these are our gases, primarily water, and that can lower temperatures as well. So if you check out this video down here, it kind of goes into the explanation of how magma is generated. Now we're going to talk about how magmas evolve. So a single volcano may extrude lavas exhibiting quite different compositions. So Bowen's reaction series and the composition of igneous rocks. So Bowen was a scientist that demonstrated that basaltic magmas cool, minerals will tend to crystallize in a systematic fashion based off of their melting points. So during crystallization, the composition of the liquid portion of the magma is continuously changing. So you're removing elements by earlier forming minerals. The silica component of the melt becomes more enriched, and so the minerals that remain in the melt chemically react and change. So this diagram shows you what Bowen's reaction series looks like. We start off with our high temperature, our first ones to crystallize, and we go down to our low temperature. So the last ones to crystallize, and it's also divided based off of your composition. So ultramafic rocks, we know we get olivine, we're going to get some pyroxene, and some calcium-rich feldspars. As those crystallize out, the whole melt becomes a little bit more mafic, less ultramafic. So then we're going to have pyroxene, amphibole, a tiny bit of biotite, and we're also going to get calcium-rich feldspars that crystallize out. Now that the melt has become less mafic, it's more intermediate to felsic. So again, as these start to crystallize out, every time something crystallizes out, it's changing the composition of the magma, and it's constantly evolving. So some ways that magma compositions change. So there's 3 different ways. We have magma differentiation, which minerals crystallize from a magma in a systematic fashion. That was Bowen's reaction series. So crystal settling causes a separation of the solid and the liquid components. The remaining melt will form a rock with a different chemical composition than the initial one. So the formation of a secondary magma from a single parent magma is called magma differentiation. So when we talk about crystal settling, it looks like something like this. These represent our individual crystals. As they're forming, they become denser, they settle out, and that changes the composition. Next, we have assimilation. So this is changing the composition by incorporating foreign matter. So a lot of these processes are happening near the surface where rocks are brittle, they're breaking off, they're getting incorporated into the magma, and that's what we see in this image right up here. Lastly, we have magma mixing, which is one magma body intrudes into another magma body, and the two mix together. So the best example I can think of is is when you're baking a cake. And you're doing a marble cake. So you have chocolate and you have vanilla, and you pour it all into the same, and you normally take your knife and you make really pretty swirly patterns. Now where you're getting that swirl, at some point those two are mixing, so it's not vanilla and it's not chocolate, but it's the two that are combined together. Alright, so partial melting and magma formation. So incomplete melting of rocks is known as partial melting. So rocks with a granitic composition are composed of minerals with the lowest melting or crystallization temperatures. So that's our quartz and our potassium feldspar. So partial melting of a rock separates the ions from minerals with lower melting temperatures from those with higher. So if you look at the image, we'll have our primary magma. So as we start with our higher melting temperatures, and we have our crystals that settle out down here, then as it's moving up, it becomes more basaltic. We'll have more crystals that settle out. Our magma then moves up, it becomes more intermediate. We have more settling out, and we'll eventually end up with a felsic magma. Alright, so we are going to do a little test your knowledge question. If all silicate minerals melted at exactly the same temperature, would magmas in different compositions even exist? No, they wouldn't, right? If it's all mixing together and all melting and forming rocks at the exact same, you would get little bits of the entire spectrum. You wouldn't have mafic or felsic because you would have the same minerals in the both types of rocks. All right, so moving on to igneous activity. So how can you recognize igneous processes that are occurring at the surface? So most igneous processes aren't visible. We can't see magma chambers. So intrusions can have a variety of shapes and sizes. So we're first going to talk about tabular bodies. So these are produced when magma is forcibly injected into a zone of weakness. So we have two examples. We have dikes, which are discordant bodies that cross-cut bedding or other structures in the surrounding rock. So if you look at this image right here, you'll see this black rock that is cutting across these layers. Now, what is cutting across it, that is the dike. So you had these horizontal layers that was cross-cut by a dike. So that was a tabular body, and it's discordant. Next, we have sills, which are concordant bodies that are nearly horizontal to bedding with other features. So if you look down here, you'll see, even though it goes up, but this is a sill. Now it's not cutting across it, so if we had our bedding layers like this, another arm just right in here, that would be an example of a sill. Now some of our massive bodies, so there's no specific structure to these, are batholiths, stocks, and laccoliths. So these are all relatively large bodies, and you can see examples of all of those down below. So mineral resources and igneous processes. So many important accumulations of metals are produced by igneous processes. So we can have mineral resources forming from magma segregation. So heavy minerals crystallize early. They settle to the lower portion of the magma chamber. And we often will get things produced from late stages magmatic processes, and we'll get pegmatites. We also get hydrothermal solutions. So these, again, hydro is water, thermal is hot. So hot metal-rich fluids are remnants of late-stage magmatic processes. So these are where we get vein deposits of gold, silver, and mercury. And we also can get it where it forms disseminated deposits. So this is where it's scattered throughout. So it'd be like taking a bag of glitter and just kind of dropping it. It's individual grains and specks all over. It's not just one single strip of it. Alright, so next steps and additional information. Make sure you complete Lab 4. Do your reading quizzes, and if you have any extra time, check out the Igneous Rocks homework in Mastering Geology, the study module, and the Essentials of Geology additional lecture information. If you have any questions, feel free to ask me. Thanks.